Hello, I'm Doug Eggert. I'm the Director of Product Management for XR integrations at Tobii Eye Tracking. I work closely with headset manufacturers and our partners to integrate Tobii Eye Tracking into augmented reality and virtual reality headsets. So what my presentation is going to focus on today is Tobii Spotlight Technology. This is an advanced eye tracking based technology that essentially allows us to extend the capabilities of the devices as well as improve end user experience. So I'll start with just a real quick background on eye tracking and how it fits into XR. So eye tracking is fundamentally it's a sensor-based technology that allows computers and devices to understand where a user is actually looking on a display. So this also unlocks the potential for the end user to start interacting with displays just using their eyes. So when we talk about XR technology, this is head-worn technology with displays that are mounted close to our face, close to our eyes, and so it's perfectly suited for eye tracking technology and the benefits that eye tracking can bring. So I'll just give a quick background on Tobii and our kind of experience with wearable technology. I think this is important for XR because we can kind of proudly state that we've been in enterprise applications for over a decade. What you're seeing here is the Tobii Pro 2 glasses, which are kind of the latest iteration of a wearable technology that's being used at Tobii Pro. And so there's a wide range of applications that these have been used for, but essentially the glasses help monitor user kind of attention and understanding where people are looking and how they're interacting in a real-world environment. And so this is basically employed into clinical and academic research, also in market and user behavior research, and understanding how basically people are kind of perceiving consumer environments. Uh, and then lastly, it's also used in essentially industrial applications. So anything from monitoring kind of skill assessment, stress levels within a working environment, safety considerations based on how someone's interacting with the work environment, all the way to basically performance assessment. And this is something that's also being used in professional sports to help athletes perform better based on these types of assessments. So now I'm going to talk more specifically about how we've kind of adapted that technology or leveraged it in XR. So when we think about the kind of we break it down into three primary pillars of value that eye tracking brings to the XR segment. So we start with better devices, then better experiences, and actionable insights. So in terms of better devices, eye tracking actually unlocks more capability out of the actual headset. So essentially, most of the eye tracking improvements are going to come from helping the display render higher quality graphics. But then there's kind of a side effect of that where we can actually kind of optimize resources on the device, and this could actually lead to weight savings, less heat generation, and of course those resources can be used to basically improve other things. And then also, when we know kind of more about where the user's eyes are within the device, we can use that gives us information about the user, so user profiles, but also whether or not the device is actually properly fit. And this, I think, is a huge thing, whether or not the user is satisfied with the device, because if it's just not fitted properly, that can have a major impact on their experience. So when I talk about kind of eye tracking, there's a lot that it can add to rendering higher quality displays or higher quality images in the display. So that kind of in and of itself presents a more realistic and immersive environment for the end user. But on top of that, of course, then we have all of the different ways of interacting within that environment. So the whole interface that's kind of unlocked with eye tracking technology adds a lot to the actual overall experience. And then lastly is actionable insights, and this is essentially where we take kind of this knowledge that we have in our history of analyzing behavior within the real world environment, and we can apply it to a virtual or mixed world environment where we can analyze basically the same thing about how users are interacting and how their attention is being focused within a virtual or mixed reality world. So actually, those are kind of the value propositions, but how do we actually deliver that to XR? So essentially, we kind of break it down into we provide the entire eye tracking system. So at the very kind of top, we have the eye tracking system design. uh, and that's actually that's kind of the foundation for integrating eye tracking into a headset. So we understand all the kind of necessary geometry, and then also the placement of the different components and where they need to go within the headset. And then lastly, we've got basically the core technology, which is our Tobii Eye Core, which provides the algorithms that are actually running on the chips in the headset uh, that actually do the calculations for the eye tracking. And this, of course, is something that's been kind of built up over, like Tobii Eye Core has existed for 16 plus years. So we're just leveraging that kind of that technology in XR. So we've basically kind of built that up over time. It's nothing new for us. It's just we're leveraging it in the XR world. And then lastly, we have our development, our SDKs, or our SDK that provides documentation that helps developers essentially develop eye tracking, see examples, and basically makes it a lot easier to get kind of up and running and to get the value out of eye tracking. So just kind of speaking more specifically to the components, what I'm just going to show here is this is just kind of an overview of what the components look like for a AR headset. And so if I just look here, this is just showing kind of a conceptual form factor where you actually see that we can tell that the components that we have today are actually kind of designed to fit in a relatively unobtrusive small form factor that's well suited for AR. So here we just see that we can see the camera placement, the LEDs, and then we've got basically the kind of down at the lower right hand side, you see where the processing is going to be. So moving on to actually VR, we've got a very similar system that leverages the same technology. So this is just showing a VR headset that has eye tracking integrated into it. So it's we see that very similar. We've got the illuminators that are in basically this ring around the eye. And then we have the camera sensors that pick up these reflections from the eye, from the light that shine from the illuminators. And then lastly, we have the eye core that runs on the actual chip. So this could be a Tobii Eye chip. It could be a third-party chip in the headset, or it could be Qualcomm Snapdragon mobile platform. Okay, so with eye tracking, what are we actually trying to do with eye tracking? How does eye tracking help address some of the big challenges in VR today? So let's first start by what are these kind of big challenges? So the first that I'd like to say is just visual quality and performance within the virtual environment. So we're basically dealing with displays that are rendering higher resolution graphics with more complex rendering techniques being added to get realistic reflections, shading, lighting, basically everything that we can do to create an immersive environment for the end user. And this, of course, is all being done with kind of the field of view always expanding to kind of get to this next level of immersion. And so as we get these kind of more realistic, photorealistic graphics and the rendering kind of capabilities behind them, we have to maintain frame rates that are going to be comfortable for the user in virtual reality. So this is a big challenge, getting better graphics while maintaining performance that is going to be comfortable for the end user in the headset. So basically, when it comes down to it, we're dealing with much more complex graphics that are being rendered remotely and need to be transferred back to the headset very quickly. So these are kind of two challenges that are somewhat intertwined. So now I'll introduce Tobii Spotlight Technology, and this is essentially an eye tracking, a high accuracy gaze-based technology that we've implemented to basically to hopefully address both issues, from the complex rendering and the visual quality to the bandwidth issues that brings when we start doing split rendering. So fundamentally, the way that Spotlight Technology, the concept that it's built around, is actually how the human vision system works. So I'll just kind of, if we look on the slide here, what it's kind of representing is this. When we look in the center of this kind of circle that I've just added to the slide, you see the fovea. And so this is actually representative of the focal point. Wherever you're looking kind of in your environment or on the display, you only see high resolution images within that foveal region. and then as kind of it moves further out, you don't actually perceive the image in high resolution, and then out in the peripheral, the only thing you really kind of catch is flickering, any kind of artifacts, or colors or fast movements. So Tobii Spotlight Technology is really kind of what we're doing is we're using a low latency, high accuracy eye tracking signal to track this foveal region. So that can be basically fed into the graphic rendering pipeline, uh, and that information can be shared, and essentially we can either be smarter about how we compress or how we actually render images. So what I'm actually showing here is this is the view inside of a virtual reality headset. And what we can actually see here in the green area, that is the foveal region. And see, it's moving around because we're using the eye tracking signal to basically track the foveal region as the user's looking around in the headset. And then the yellow area shows that's essentially kind of the outer edges of the foveal region. And then anywhere outside of that is essentially that's your periphery. So in the context of foveated rendering, based on this Spotlight technology, all we really need to do is render that green circle in high resolution. And then basically we can super sample the rest of the display. So that's the whole concept behind foveated rendering. So we've actually done some benchmark tests with Tobii Spotlight technology for foveated rendering. We've used a Vive Pro Eye to essentially do the benchmarking test on a tethered device that supports Tobii Eye Tracking today, and then also the Pico Neo 2 Eye, which is a standalone device that also supports eye tracking. So both of these devices, since one is tethered, one is standalone, they have different processors. So we've tried to kind of basically benchmark all of our different kind of supported XR form factors. So not only do we have different processors, but also we tested with different game engines. So different 3D engines. So we're basically applying the different foveation techniques of both Snapdragon and NVIDIA VRS. So Snapdragon, the Qualcomm Snapdragon Adreno foveation, and NVIDIA VRS foveation in both Unreal and Unity game engines. And you can see here in these benchmarking results that the results that we saw, there was a pretty compelling reduction in the shading load that we saw basically kind of across the board. So on this slide, we can actually see the benchmark results from the Vive Pro Eye with NVIDIA, using NVIDIA VRS advanced rendering technique, and the Unreal Engine with Tobii Eye Tracking enabled. So when we look at this actual chart, on the left-hand side, we see the rendering load without VRS enabled. So the rendering load on the GPU was right under 25%. Now in this similar situation, we're talking the same kind of graphical rendering load. We see when we turn on dynamic foveated rendering based on Spotlight technology, there's this 57% reduction in the average GPU load. So essentially, we're basically freeing up those resources with foveated rendering turned on. But then, more importantly, when we look at the frame rate on the right-hand side here, you'll notice that this kind of light blue that we've got, this light blue line, that's the frame rate that we're maintaining with foveated rendering turned on. Then with the dark blue, this is foveated rendering turned off in basically the same rendering situation. And we see the frame rate is nice and steady with foveated rendering turned on, right at about 90 frames per second, which is going to be a pretty comfortable user experience. But then as soon as we turn it off, then the frame rate is this dark blue line. It's much less consistent, and it's also dropping below 60 frames per second quite frequently. And so it's absolutely going to affect the end user experience. So this slide is these are the results that we had with the Pico Neo 2 Eye and using Qualcomm Snapdragon Adreno foveation in a Unity 3D environment, a Unity built 3D environment with eye tracking enabled. So when we look at this chart kind of on the left hand side, we can see with full rendering, the GPU shading load was right at about 78%. Then as soon as we turn the foveated rendering on, the average GPU load drops down to 26%. So this is basically freeing up headroom with the GPU just by using this foveated rendering technique. And again, I'll talk about the frame rate. And if we look here on the right-hand side, so we've got the 72% reduction in load. But then on the right-hand side here, we've got essentially these two lines. One represents the yellow here is with foveated rendering turned on with this eye tracking signal from Spotlight. And then the light blue is full rendering. So we can see that with foveated rendering turned on, we're basically maintaining this 75 frames per second. So it's going to be a nice kind of comfortable user experience. Whereas when we turn it off and we're doing the full rendering, it's much less consistent, and it's also dropping again below the 60 frames per second for basically a majority of the test, and that should be a pretty uncomfortable user experience. So this is actually a pretty, you could say it's oversimplified kind of bar chart, but what it really does is it shows kind of the trade-offs of basically implementing advanced rendering techniques and how that can affect your frame rate, and basically this kind of give-take. Do we want faster frame rates or higher quality visuals? So on the left-hand side here with this kind of light blue chart, we see, okay, with the standard VR scene, we can maintain 90 frames per second. Then we start adding these advanced rendering techniques to give a more realistic environment, and then suddenly our frame rate drops. But on the right-hand side here with the blue chart with improved visual quality and dynamic foveated rendering, this is showing when we turn foveated rendering on, we've got the advanced rendering techniques. The fact that we're just rendering that foveal region in high resolution, this is saving us the GPU headroom. And so basically we get the best of both worlds. We get high visual quality from the graphics, but then also the performance we need to maintain a good user experience. So this graph is actually a kind of what we're doing here is we're kind of looking into the future. If the display technology stays similar to how it is today, but we just start increasing the resolution, we're going to be rendering more pixels. And this chart kind of shows how as display resolution increases, so does the number of pixels that need to be rendered, either in a full rendering for this dark blue, the no VRS, or for fixed foveated rendering. So that's if you're just doing kind of a big kind of not an eye tracking enabled where you're really focusing the foveal region, but you're just using kind of an area of the screen. And then dynamic foveated rendering where we're actually using that eye tracking signal to just focus on the foveal region. So you can see here that as the number of pixels increases dramatically with the resolution, things stay relatively stable with dynamic foveated rendering because the foveal region is not going to increase. So we're always going to be kind of maximizing, we're always going to be focused on rendering high resolution just in the foveal region. So the rest of the display can continue to get kind of increase in resolution without taking this big kind of performance hit. Okay, so now I'm going to kind of switch gears a little bit and start talking and introduce Tobii Spotlight Technology for foveated transport. So I kind of mentioned at the beginning, foveated renderings where we're using this identifying the foveal region, and we're only rendering graphics in high resolution within the foveal region. When we talk foveated transport, this is actually a method of compression that we're putting on the image so that we can compress areas that are outside of the foveal region. So basically the reason that this technology is becoming important is because we're seeing more and more kind of split rendering technology and capabilities being introduced into XR. And so with split rendering, the rendering is actually happening off of the headset, and so we really need to find ways to get these high quality images from either the local GPU that they're being rendered on, or if it could be a cloud or 5G enabled edge computing situation. There's some way that we're generating these high quality images, but they have to be compressed, or else we're going to be dealing with bandwidth limitations. So I'm going to play a quick video it's a 30-second introduction video that we've done to basically provide a real quick overview of the concept behind Tobii Spotlight technology for foveated transport.
Bandwidth to the headset is a bottleneck within VR, but guess what? Nature has a perfect solution. Your eyes work like this. The direct focus is kept sharp. We call this fovea. Everything around is blurred. Let's apply this to VR. Eye gaze is tracked by headset sensors. This fovea data is sent to the GPU, next rendered, warped, and additionally compressed. This smaller image stream zips through the pipeline back to the headset, minimizing bandwidth and latencies, while delivering a visually stunning and immersive experience. Perfect for local, cloud, and edge-enabled split rendering, whether over 5G, Wi-Fi, or cable. Headsets and user experience are enhanced with Tobii Spotlight for foveated transport.
Okay, so that's a great video to kind of summarize the concept behind Tobii Spotlight Technology and what we're developing for foveated transport. What I'd like to do, though, is just kind of go a little bit more into the detail on the compression step so that you can kind of understand what we're actually doing when we say what we're doing prior to transport to actually save bandwidth. Okay, so if we take the split rendering scenario, this image that we're seeing here in step 1. This represents a frame that's being rendered basically somewhere other than the headset. So we have a fully rendered frame. And now we're using basically this warp map. If we look at the square in the center, this represents the foveal region. So this is the area that we really, this is where we're using eye tracking to identify where the user is actually looking within an image. And so that's where we need to make sure that we maintain the full high resolution, high fidelity quality of that area of the image. So that's identified. That's when we do this warp map, then we're basically identifying where we can apply this warp and compression to reduce the size of the image that's actually sent to the headset. So we can see here in step 3, we've warped and compressed the image. So we're essentially reducing the size of the image, the frame that needs to be sent to the headset. That's sent to the headset decompresses, unwarps the image, and now we can see that we're displaying the full-size image, but then in the areas that we're basically kind of the compressed areas are not being rendered as high quality because they're actually not perceivable to the end user, but this center area, this foveal region where the user is looking, is rendered in high resolution. So we basically reduce the size of the image that needs to be sent, and if this is done using a high quality, low latency eye tracking signal, and it's mapped exactly to where the user is looking, then there will be no perceived hit to the quality of the image, even though the size has been reduced for each frame. So we're saving on bandwidth with absolutely no kind of visually perceivable hit to the quality for the end user. So essentially the benefits that we're seeking to get out of foveated transport are to optimize the rendering pipeline. And to do this, we're actually applying a compression after the image is rendered, but then we can increase these compression ratios even before the images are sent to the video encoder. So right now we're seeing about 6-to-1 compression ratios before the video encoding, and hoping to even get more out of it. And so this is actually going to be reducing latency to the headset and reducing bandwidth. So the benefits are that with whatever bandwidth you're dealing with, you'll be able to get higher quality, or if you're trying to just save on bandwidth, you'll be able to reduce bandwidth usage. So thank you very much for your time. Again, I'm Doug Eggert, and I'm the Director of Product Management for XR OEM Integrations. So feel free to reach out to me for any questions about what Tobii Spotlight and what Tobii Eye Tracking in general can bring to your XR headset, if that's something that you're working on developing. I've also got some links here to some useful information. So we've got the link to our OEM offering page. So this is basically kind of a summary of what I talked about at the beginning of the presentation. We've got a nice website that explains what is included in the basically the eye tracking system that we provide to headset OEMs. Then we've got a web page that describes a little bit more in detail the Tobii Spotlight technology. Then last, we've got a really cool developer website that has you can get access to the SDKs for developing eye tracking into your own applications, and then also all of our documentation, and there's some really cool examples and demonstrations of eye tracking use cases. Thank you very much for your time, and I'm looking forward to the Q&A session. See you soon. Bye.